Hello, everyone. So, welcome to Unit 5. We're going to go through some calculus concepts with exponential and logarithmic functions, okay? So we just finished trig, and now we'll move into exponents and logs. And the first couple of lessons here are going to feel very similar to the first couple of lessons of trig. What did we first do when we started our trig unit? We looked at various limits of trig functions, and that's what we're going to do today. We're going to look at various limits of log functions. Then we'll turn our attention to some specific derivatives for exponential functions and for logarithmic functions and do some work in that, okay? Then we've got some other fun stuff planned too, but I won't get too far ahead of myself. So today we're going to do limits of exponential and logarithmic functions, okay? So the first thing we want to do is just kind of get back into our brain, kind of a picture of what some of these graphs look like. So we want to take a look at kind of three of the main graphs that we talked about in 30-1, that being an exponential growing graph, an exponential decaying graph, and an logarithmic growing graph, okay? If you happen to be a student taking 30-1 and 31 concurrently, this may be a moment where we're a little ahead of your knowledge in 30-1. So take a look at, you can just quickly look at some of my 30-1 videos on this subject just to kind of brush yourself up, okay? Okay, so you should feel very comfortable that when you are given this equation, y equals a to the x, where a is greater than 1, to say that that is a growing exponential graph. Okay, and a growing exponential graph looks something like that. And now the domain of that fella is going to be a member of the reals, but we'll say -infinity to infinity. The range will be 0 to infinity. The horizontal asymptote will be at y equals 0, and there won't be a vertical asymptote. Okay, so those are all the parameters that I want you thinking about with that picture. Then if I switched it to still an exponential graph, but now I'm saying a is between 0 and 1, so that means a is a fraction, then you're going to tell me that this is a decaying exponential graph, and a decaying exponential graph will look like that, okay? So the domain hasn't changed. It's still going to be -infinity to infinity. The range hasn't changed. It's still going to be 0 to infinity. The horizontal asymptote hasn't changed. It'll just still be at y equals 0, and the vertical asymptote will still be none. Okay. All right, then we're going to move to a log graph. Now this is a log graph that again has the base greater than 1, so it's growing right now. Okay, so a log graph that's growing, you'll recall from 30-1, looks something like that. Now the domain and range flip from the domain and range of the exponential function because remember that log functions are inverses of exponential functions, right? So everything that was x is now going to become y, and everything that was y is now going to become x. So the domain of this guy is actually going to be 0 to infinity, and the range will be -infinity to infinity. Then we won't have a horizontal asymptote. This guy will continue to increase all the way, like as x approaches infinity, y will also approach infinity. And then there is a vertical asymptote for this guy at x equals 0. Okay, so now we also want to introduce Euler's number. Now we talked very, very briefly about Euler's number in 30-1. We didn't do a whole lot with it, but we have some special numbers in maths. There's special irrational numbers like pi. I is actually not an irrational. That's not in this list. It's an unreal number, but that's for a conversation for another day. √2 and e. E is Euler's number. Okay, and it's defined as the limit as x approaches 0 of 1 plus x over 1, 1 plus x all to the 1 over x, okay? And it is an irrational number. E is 2.718, blah, 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 blah. If you'd like to figure out what it is, you can go, you have an e to the x button on your calculator. It's usually going to be the second function of your ln button. And if you just put e to the 1 in there, that will give you a few more decimal places as to what Euler's number actually is, okay? It's 2.718281828 is as far as my calculator will go, okay? Okay, so recall x equals log base a of y is the same as y equals a to the x. So now what I'm recalling here is how to switch from an equation that is in logarithmic form to an equation that is in exponential form. So you'll remember from last semester in 30-1, the base becomes the base. Okay, so the base of the log will become the base of the exponent. The dude that was by himself, he's free, is now locked in. So he's now locked in as the exponent. And the dude that was locked in with the log is now free. Okay, and then it works the other way too. If I wanted to go from the exponential form back to the logarithmic form, I'd have that same conversation. The base becomes the base. The dude that's locked is now going to be the dude that's free. And the dude that was free is now going to be the dude that was locked. Okay. So now with that thought, we also want to take a look at log base e. Okay, e being Euler's number. So we can say that if we had an equation that was x equals log base e of y, we can switch that to exponential form. That's the exact same way. And that's going to be y equals e to the x. Okay, y equals e to the x. Now, we can replace log base e with ln. Okay, ln stands for the natural log. Okay, and the natural log is defined as log base e. Okay, it's just a special base and it has a special name then. And so it will be the same thing to say that x equals ln y is the same as y equals e to the x. Okay, so essentially when we're looking at this guy, we're kind of doing two things. We're taking that x equals ln y and we're gonna, in our head, convert it back to log base e of y and then switch it to exponential form. Okay, so log base e of y is called the natural log of y and is written as ln y. Okay? Okay. So if I was to graph y equals e to the x, I would get a graph that looks something like this. And if I was to compare that to y equals ln to the x, I would get a graph that looks something like this. Now, let me just go back for a second just to, again, prove my point, if it were. Y equals e to the x, okay, is the same as x equals ln y. So in this picture here, I didn't graph x equals ln y. Just gonna go back, I'm gonna move ahead for you here for a sec. I graphed y equals ln x. Okay, so what I want you to see there is if this says y equals ln x, these guys are actually inverses of each other. Okay, I would say y equals ln x is the same as y equals log base e of x. And then if I was to take the inverse of that, it'd be x equals log base e of y, and then I'd switch it to exponential form and get y equals e to the x. Okay, so my big, long, convoluted conversation here is to say, I want you to look at these two equations. I know I already showed you the graph, but look at these two equations, and I want you to be comfortable to say, yes, these two equations are inverses of each other. Then when you look at the graph, I'll get my ink turned off here. When you look at the graph of both of these again, y equals e to the x and y equals ln x, you can see that these are in fact inverses of each other. These are reflections, diagonal reflections against the line y equals 0. Okay? All right. So now what we want to do is just work through some limits and just see how you're feeling about them, okay? So y equals a to the x is what we're given, where a is greater than 1. Determine the following limit. So if x was approaching infinity, if I start putting a really big number in here, we've actually already talked about that when we started talking about limits in general. That limit will not exist, right? As I continue to put a big number in for x, my answer is just going to come out to be bigger and bigger and bigger, okay? So it approaches infinity. But if I put negative infinity in for x, that's going to approach 0. That was one of the conversations we've had previously. And if I'm putting 0 in for x, that limit will approach 1. So those ones should all feel relatively comfortable for you, okay? Okay, now we're going to take a look at same graph, but we're going to just add some parameters around it. So now we're looking at the limit of, as x approaches infinity, of a to the x plus 1. So again, this first guy, if I'm approaching infinity, that a to the x is just going to get bigger and bigger and bigger and bigger. So the limit won't exist. It approaches infinity. Okay. Again, if I put negative infinity in for x, if I approach negative infinity, a to the x is going to become 0. So I'm going to be left with 1. And then I'm looking at a to the x plus 1, all as the exponent. Well, if I stick infinity in for x, it doesn't really matter that I'm adding 1. If it was just going to get bigger and bigger and bigger anyway, it's just infinity plus 1 now. It's just going to get bigger and bigger and bigger. So that one also does not exist and approaches infinity. Okay. All right. So now try these guys. I'm assuming you're pausing me and trying these yourself, of course. Just for clarification, as I go through this note, you should always be trying these things before you listen to the answer. Okay, so the limit of a to the x plus 1 as x approaches 0. Well, as x approaches 0, like I can do direct substitution here, right? As x approaches 0, I'm left with a to the 1, and that'll be a. So that will be a. The limit of 2x plus 2 to the x plus 1 as x approaches 0 will end up being 2 to the 1, which is 2. And the limit of 7 pi over 4 to the 7x plus 1 as x approaches 0. Again, if I'm substituting 0 in here, I'm going to end up with 7 pi over 4 to the 1, which is just 7 pi over 4. So the limit is 7 pi over 4. Okay. Okay. Now let's take a look at the limit as x approaches negative infinity of 2 to the negative 3 times x. Now here you want to think about that. If I put negative infinity in here, I get negative 3 times negative infinity. Negative times negative is actually positive, so that gives me 3 times infinity. And so there will be no limit there. It'll just continue to increase. It approaches infinity. Okay. The limit of e to the x as x approaches 0 from the right. So if I'm approaching 0 from the right, I might want to plug in 0.1, 0.01, 0.0001. Okay, that's going to get you 1. And then the limit of ln x as x approaches infinity. Well, I want you to think about that guy for a second. I've already showed you a picture of ln x, and I want you to always remember that ln x is the same as log base e of x. So it's just a log graph. And so if I showed you a log graph looks like that, right? So as x approaches infinity, this guy's not approaching any asymptote. This will always increase, okay? So for this guy, there is no limit. It does not exist, but it approaches infinity. Okay? Okay, so now we're gonna stay on this, this natural log graph. If I had the natural log of x minus 4, visually, I'm just taking this and moving it 4 to the right, right? That's all that says. So again, if I'm approaching infinity, nothing's really changed from the last question. Just because this graph has been shifted 4 right, it's not going to change the fact that my y values continue to increase as x approaches infinity. So it does not exist. It approaches infinity. Okay. But on the next guy, as I approach 4 from the left, or sorry, from the right, as I approach 4 from the right, so I could plug in 4.1, 4.01, 4.001, 4.0001, and test that out. Okay, you should be getting the fact that you're going to negative infinity there. And visually, what I want you to see there, if I took this away for a sec and just went, like, I want you to understand that if that had been, if that was x minus 4, there's a vertical asymptote at 4, right? You should feel comfortable enough about that just from your 30-1 knowledge. So this graph is going to go like this now. where this is x equals 4. So it makes sense that as I approach 4 from the right, those numbers, my y values are going to get bigger and bigger and bigger in a negative direction and tell me that I'm approaching negative infinity. Okay. Okay, and then the limit as x approaches infinity of 4 to the x over 2 minus x. So now we have a little bit more of a complicated exponent there. If I'm approaching infinity and I've got a rational exponent, we can divide everything by the highest power in the denominator, okay? And so I can look at this and say, okay, I'll divide everything here by x. X over x is going to give me 1. 2 over x is going to give me 0 and minus 1. Okay, so that ends up being 4 to the negative 1. Okay, because 0 minus 1 is negative 1 and 1 over negative 1 is negative 1. So then 4 to the negative 1 will give me 1 over 4. So the limit of that guy will be 1 over 4. Okay. Awesome. All right, so that's it for today. You can get going on your homework. And as always, if you have any questions, make sure you connect with me. And next lesson, we'll start talking about some derivatives. Okay, take care, guys.